Hello, I'm Charles Sobczak, manager of the FPGA Workbench team here at Concurrent Realtime, and today I'm going to be doing a demo showing our FPGA Workbench NIos IP module. So what is the NIos IP module? Specifically, it's Altera's 32-bit soft-core general processor using the RISC-V technology. It's a very powerful software processor. It has integer multiplying divide and a floating point unit. But additionally, one of the huge benefits that we have, as you can see from this block diagram, is we have the processor fully integrated into our FPGA Workbench environment and our FPGA architecture. So the customer has direct access to all of the memory units inside of our FPGA, so the register interface. So whether it's using the NIOS to flash new executable code inside the NIOS processor, or whether it's taking analog inputs or outputs, or working with the shared memory, you'll have full access to all of that. So what are our FPGA cards? So we have a number of FPGA cards, and here we're showing two. We have the ARIA5 on the one hand, and then we have the ARIA10, which we'll be using for this demo today, and we'll be using one of the analog daughter cards. So how do we start our development? So first we should really just come up with a basic, from a systems level perspective, a basic block diagram and show the inputs and the outputs, the parameters and the test points of the module. Additionally, it's good to decide what part of the algorithm would we want inside the NIOS embedded software and what would we want in the FPGA fabric. Certainly we could put the multiply and we could write our own AWGen module inside the C code for the NIOS, but in this case we're going to leverage our own IP modules. So here's a block diagram showing a digital automatic gain control. And we're going to be doing a very simple peak detect algorithm, but we've also included our additive white Gaussian noise IP module inside the fabric to show that we can very easily add non-idealities and take our basic testing to be able to show signal to noise and performance testing and evaluation. So now let's take this block diagram and show it inside the FPGA workbench. So I'm going to zoom in on the next slide, but this is initially just to show the test points that we're going to be using on the oscope. So if we start on the left-hand side here, we have the yellow signal, which will be from a wave generator, a 10 kilohertz signal, and we will vary the amplitude. The next is the green signal, which is after the mux and after we add the noise. And then we will have the blue signal, which will be after the gain control. And then we will also be displaying the gain that is being fed back and multiplied to be scaling the signal. Okay, now let's zoom in on the left-hand side of the diagram. So first, we're going to show here that we can do lots of things in the workbench. In this case, we have our end-phase wave generator input into a mux with also an analog input. So we could switch between them. So if we want to do an idealized internal signal, we could use the end-phase wave generator. In this case, we're doing an external signal generator inside, being fed in a ADC and then going into this mux. Next, we're going to feed that mux into an adder, which is going to add into AWGN, and we'll display that signal in green. And now we're going to shift to the right-hand side of the diagram. And what I initially wanted to show again was just how flexible it is for us to for the user, for the customer to see all of the internal registers. So there's internal registers for reading data in, registers for writing, and shared memory. And those registers can be tied directly to wires, to analog outputs, and they can also be tied to the register interface. So in this case, we're going to look at two different registers, and the location of the registers for the NIOS in this case is at 20000 hex, and we're going to look at 20018 here, which is the AGC gain, and we see the IO write command. So inside the user NIOS, we're estimating the gain of the signal, and we're going to display it in this register. And secondly, we're going to show the AGC step size at 2001C here. And we're going to be just showing very quickly how we could switch between, say, a coarse AGC step size and a fine AGC step size. So now that gain signal is also being fed back and multiplied inside the FPGA fabric with hardened multipliers, and then we're going to display the signal on the oscope. Okay, so let's quickly take a look at what the C code looks like. So inside the C code, we have our standard includes math.h and io.h. We also have the parameter instantiations. Here we're using some shorts and some signed shorts. Now here's the top of the while code. And again, this is a very simple peak detector. And first we have an IO read. We're reading the signal from the ADC input into the NIOS so that we can start to estimate the peak voltage of the signal. And then here is the step size that we will switch between a fine adjustment and a coarse adjustment to show how easily we can shorten the development time between writing C code and being actually testing it on the bench. And here is that portion of the peak detection algorithm where basically what we're doing is we're running this loop every 32,000 cycles. And the first thing that we do is, I guess, we reset and we update the gain, and then we continuously calculate the peak once per 32,000 cycles. Well, continuously updating the peak, but then updating the gain once. So now we're gonna scroll down and we see this is the portion of the code where we use the AGC gain. If we're above the target amplitude, we step the gain down. If we're below the target amplitude, we step the gain up. And again, ideally you'd want to use some kind of hysteresis or convert to dB log scale. But this is just some very basic code to show really, again, how quickly it is to shorten your development feedback loop for a software engineer. So now I wanted to show again the interface with the registers and how easy it is to connect and see your data. We'll focus on the two of them, the AGC gain, which is the one above, and then the AGC step size. All right, so lastly, one more time, we're going to have the yellow as the input signal, the green is the output of the AWGN, and the blue is the output of the gain, and the pink magenta signal will be the gain that's being fed back. Now, let's jump into our Linux workstation, and I'm going to go around in a counterclockwise manner and explain what each of these windows are before I start the demo. So in the top left-hand side, this is the NIOS shell for the source code. So the two things that we'll be doing here is we will be looking at the source code. So I'll jump in right quick. And we can see here's the source code, and we will be making a quick edit to it. And we'll be doing the make so that we can upload it. Now to upload it, we'll be using FPGA Workbench. So this is fully integrated. After you've made your file, you write that executable file to the NIOS, and you're immediately running the new code. So that'll be the second thing that we will be doing. Now, if we go down, this will be the register display. So again, that's 20,000 hex. Right now, we see that there's nothing in that memory because we haven't programmed anything. And then if we go to the bottom right-hand side, these are the four signals that I've been describing. The yellow signal is the input signal. The green signal is the output of the mux plus the AWGN. The blue is after the gain, and then the pink is the gain signal being fed back. And the top right window, is our software development kit, where we will need to start programming our IP modules and program some of the aspects of the architecture. So let's jump right into that. The first thing that we are going to do is we're going to program the clocks. And additionally, I'm going to program the clocks for the NIOS. We have control where you can have separate clocks for IPs or the NIOSs. Lots of flexibility and control in that perspective. And now I'm going to turn the DACs on and the ADCs. All right, so the DACs and the ADCs are on, and I actually had the mux on, so I'm going to quickly turn the mux off so I can go through this flow seamlessly. Okay, so I turned the mux off, and we saw the green signal disappear. So everything's on. So The first thing that we're going to do is we're going to turn the muxes on. So you're going to see that signal reappear. And it's very easy. There's a help. If you do dash on the SDK, you see all the information on the help. To switch the mux on, we just switch that I from 0 to 1, and it's going to switch from that top input signal to the bottom input signal. The top was the internal end phase, and the external is that wavegen. So now we see the delayed version of the wavegen coming in. Next, we're going to do the additive white Gaussian noise signal. So let's do that. C0, B0, and we're not going to program any specific seed in this case. So first we're going to program that. And then now we're going to program the noise variance. So I'm just going to set that noise variance to 1. And you see quite a bit of noise now coming through. So if you wanted to do SNR testing, this is really a fabulous way to do it. You can sweep your noise variance, or you could also keep your noise variance constant and then adjust your signal power. Okay, so we have the signal plus noise coming through. Now we need to turn on the NIOS. So let's program the NIOS, and we already have that code set up. So I am going to browse to the C code here, and we have it here. And I'm going to name it AGC0, and I'm going to flash. Bang, and there it is. I'm going to disconnect and reconnect so that we can see the current software version here has been updated to AGC0. And we saw the blue signal, which is the output of the gain. So this is fully functioning now. So if I go in the bottom left-hand window, I'm going to run the display, and we see 20,000 hex was the input signal, and then the two that we really wanted to focus on was 20018, which is the gain, and 2001C, which is the AGC step size, which we have fixed at 1. So now we are going to adjust the voltage of the input signal to, it was 20 volts peak to peak, so we're going to switch it to 4 volts peak to peak. And we see the yellow and the green signal, which are the inputs before the gain control, and then we're seeing the blue signal increase, which is that gain control signal. Now that is quite a bit of noise, so I am going to reduce the noise variance a little bit here, which is quite easy to do. So I'm going to drop it to, let's make it a quarter. Okay, cool. So we're seeing the signal, the digital gain control using the peak detector slowly amplify the signal, which is fantastic. But again, it's very slow. And if we looked in the left-hand window in the display, we see the 1.8 offset. We see the gain has increased considerably. So now I'm going to push this all the way back into clip, 20 volts peak to peak. And now we've clipped the signal. And we see in the display, we see the gain coming down in the 20018. And we see in the window, the oscilloscope window, we see the blue signal slowly coming back down to being in range. So our algorithm is working. It's working pretty good. Now, while we wait for that signal to get back in range, we are going to jump into our C code. On the left-hand window, we are going to make that edit to change the step size from a very fine setting to a coarse setting. So let's make it, we'll make it 5 for an example. And then we are going to, I'll show you the run script, which is basically just making the file, the app file that we just edited. So let's run the temp script, and it's building that. So we made a change to the C code. We've built it. Now let's quickly throw this back into the NIOS, and we're going to see immediately that 1C offset register get updated. And I'm going to change the name to AGC1. We already have it connected, so we're going to flash it. Boom, there it is immediately. See how fast that is. I'm going to disconnect and reconnect so we can see that the current software is updated. And now we've updated that AGC step size to 5, so it's a much coarser change. And we are going to look now at the scope again. And we are going to change the voltage to 4, and you're going to see 4 volts peak to peak, and we're going to see it's going to track much more quickly. Okay, so I change it to 4, and wow, see, it's got that coarse adjustment, but you're going to see some potential error in the estimate as it might bounce around a little bit. And now let's throw it back into clip. It jumped 20 volts peak to peak, and we see that gain coming back down to around 80 hex in the 1.8 offset, which is close to a 1-to-1 gain. So that is an example of using our NIos IP module, which really helps the customer shorten that software, embedded software feedback loop from coming up with the algorithm to creating your C code to uploading your C code onto the FPGA and then testing it. Thank you very much and see you soon.